good morning. So as we were discussing in the last class, once we are representing the dispersion equation like as like a 1 plus summation of the rational polynomials, then we can able to express, then from solving this we can able to get the band boundaries, and also we can able to identify whether the peaks exist in the attenuation band or not. So for example, if you see that band boundaries are calculated, so band boundaries were calculated like this way, that because as the cos mu has the range from -1 to 1, so we can substitute it like -1 less than equal to 1 plus r omega square by q square less than equal to 1. So we can write it -2 less than equal to r omega square q omega square less than equal to 0. So band boundaries are once r omega square plus 2q omega square is equal to 0 and r omega square equal to 0. Once these two cases are happening, then it is giving the band boundaries. And when we will have the peaks in the attenuation band, so peaks in attenuation when the q of omega square that is equal to 0. Because what will happen, q of omega square, once q of omega square becomes 0, then you can think that this quantity cos mu, means once the q of omega square becomes 0, then r omega square by q of omega square will tends to infinity. So then plus 1, it also tends to infinity. So your cos mu will always out of the range, like from -1 to +1, it is always going out of the range. So you will definitely get a attenuation band in that region, and q of omega square is 0. So that gives you the peaks in attenuation band if that exists. So let's see for case of a monoatomic chain. So in case of a monoatomic chain, if we see in case of a monoatomic chain, our dispersion relationship is cos mu equal to m omega square by k. That is my relationship. That's a dispersion relation, or we can call it as like simply eta square. So what we can say, that if I try to write it in terms of like r of omega square divided by q of omega square, or r of eta square divided by q of eta square, then I can write it. So if this thing can be written in this form, then what is my r of eta square? So r of eta square equal to eta square minus 1, and q of eta square is equal to 1. So what are the band boundaries coming? So if you see, oh sorry, this one is wrong. So 1 minus this one, so eta square will be minus this, sorry. So eta square and this one, so this will be 1 minus eta square. So if I write the 1 minus eta square into this, so I can write it in this form. So now from here, if I try to solve the first equation, so this is maybe equation number 1, equation number 2, and equation number 3. So if I solve equation number 1, solution of equation number 1 is telling me minus eta square plus 2 should be equal to 0. So this gives me eta square equal to 2. Okay, and second equation is giving me minus eta square equal to 0. So minus eta square equal to 0, that gives me eta square equal to 0. Okay, fine. So and q of eta, and then so this is from equation 1. So this is from equation 1, and this is from equation 2. These two things we are getting. So here output is eta equal to root 2. I am not taking plus minus because obviously the negative side of eta we are not considering. That's not a real type of thing, and here we can see eta equal to 0. Now if we try to recall the band structure, so dispersion diagram, we can see that this will go up, eta equal to root 2, we will have the band gap. Simple. And then it is starting that. So one side eta equal to 0, another side equal to root 2. We can easily able to see that we are getting this thing. Now what happened? Can we able to get any peaks in attenuation band? The question is, so we can see that 1, so q is always become 1, so it cannot be equal to 0. So q of eta square is equal to 1, which cannot be 0. So no attenuation band, so no attenuation peak. And that also we can able to confirm from our dispersion diagram that we will not get any attenuation peak in case of the monoatomic chain. Now suppose if we are doing it for the mass in mass chain, we can see like this. The mass in mass chain is coming. So this is my K1, this is my M1, and internally if we think, this is my M2, this is my K2. So what is the dispersion relationship? So the dispersion relationships, if you think, cos mu equal to 1 minus eta square kappa by 2 theta into 1 plus theta divided by 1 minus eta square. Or if we write it like cos mu equal to 1 plus sorry 1 minus like m effective divided by k effective. So what is the m effective? M effective will be m1 into 1 plus theta divided by 1 minus eta 2 square eta square. Okay, so that way we can get it. So if I just do it little bit, and ke equal to k1, that we know. So now if we substitute these two things here, then my cos of mu will becoming 1 minus omega square divided by k1 m1 into 1 plus theta divided by 1 minus eta square. So this one will become in that same way, that like kappa divided by 2 theta into eta square into 1 plus theta by 1 minus eta square. Okay, so now if we think, we are again rewriting it, that cos mu equal to 1 plus r of eta square divided by q of eta square. Okay, so what will be my r? Now you can think 1 and 1, forget it. So what is by r eta square divided by q eta square? So r eta square by q eta square will be minus k kappa by 2 theta eta square into 1 plus theta divided by 1 minus eta square. Now we cannot leave it like this way, so we have to do what? K by 2 theta is like a constant term, so it is common, we can take it. Now here it can be 1 minus eta square, 1 minus eta square plus theta. So we can write it minus k by 2 theta, then we can get it at the top 1 plus theta minus eta square. Okay, so this is coming here into multiplied by eta square. So what can I say? What is my r eta square? So my r of eta square is basically k by 2 theta, then one plus theta square perfect. That's my this one. And what is q of eta square? That will be 1 minus eta square. So we got these two terms. Now for the band boundary, what is coming here? So for band boundary, so this is my r square eta square. So if I try to calculate the band boundary, what I will get? I will get the band boundary as r eta square plus 2q eta square, that is equal to 0. So that's my first equation. So I will get it k by 2 theta into 1 plus theta eta square plus k by 2 theta eta to the power 4 plus 2 minus 2 eta square, that is equal to 0. So that's one equation. So now if you see in this equation, so that is one equation number 1, and we will have another equation, that is r eta square, that is equal to 0. So now if you think r eta square, that is equal to 0, so you will get it minus kappa by 2 theta into 1 plus theta eta square plus kappa by 2 theta into eta to the power 4, that is equal to 0. Okay, so we will get this is from the second equation. And also what gives me from that eta square equal to 0, so that's the peak of attenuation band. So this is the band boundary, this is the band boundary. So band boundaries, we will get this equation, first equation, second equation, so we will get that. And this is for the peaks in attenuation band, peaks in attenuation. So that is q equal to 0. So what we can easily say, that is 1 minus eta square, that is equal to 0. So peaks will be at eta square equal to 1. So eta equal to 1, we will have the attenuation peak. Okay, and these two gives me the two condition of the band. Now let's see what we are getting from here. So we can see that this equation is something like a eta to the power 4 plus b eta square plus c, that is equal to 0. So this is a quadratic equation of eta square. So what will be the eta square? Eta square will be minus b plus minus root over of b square minus 4ac divided by 2a, that we can able to get from here. And what about this one? This one is simply telling eta square minus 1 plus theta eta square, that is equal to 0, because I can just take k of eta out, so we will get it. So here we can get that solution like eta square equal to 1 plus theta comma 0. 0 can be one solution, or another solution is root over of 1 plus this one. So I can say eta equal to root over of 1 plus theta can be one point, and 0 is one side. So if you see the band structure very carefully, so it is going up, then from here we will have it in the imaginary portion, again it will go up, and again it starts from here. So here we will get the four boundaries. One boundary is this is actually this point, root over of 1 plus theta. Okay, this point is here, this is equal to 1, because that is the peak in the attenuation band. So I think we all remember this portion is like showing the attenuation, and this portion is showing the propagation. So we can see that peak in the attenuation 1. If you see in the last case, we do not have any peak in the attenuation, because we are getting q equal to 1. Q equal to 1 cannot be 0, so it is not giving any attenuation, any peak in the attenuation band. Now here peak in the attenuation band is possible, because we have an expression, and once we make it 0, so we can able to find out, okay, where the peak can be possible. So we will get it 1. Nice. Now here if we are coming, so this point we can also able to see that this is 1 plus theta. 1 plus theta is coming here. Now yes, so this one gives me the 2 point. What are these 2 point? This is like eta equal to f1 comma f2. So this is my f1 point, and this point is my f2. Okay, so we will get these 2 point, f1 and f2, from that. Okay, so this way we can able to solve that whole thing. So you will see that how we can easily able to locate where the peaks are coming, and how we can able to go how we can able to solve that. Now suppose if we are taking like a normal INM, so whatever you are like solving this type of thing, you can able to calculate what is the R, what is the Q, and that will reveals the complete dispersion diagram in a very simplified manner. You can easily able to trace where the peaks are, when the peaks can be merged, what their analytical equations should be for the peak margin, band margin, all those things can be easily thought from here. So you can see here, like we take a case of the INMNS system and we wrote the MATLAB code completely for solving it. I'm not going into the detail of the MATLAB code. So now if you see here, so this is the imaginary part, this is the real part, and you can see that these peaks are coming. So there are the 3 peaks coming in the attenuation level. So 3 attenuation peaks we can able to see, and there are the band boundaries are also coming. Now you see how we can able to so we just change some parameter like eta r1 we are changing, and we can see that how the different cases can be seen. So this is like a overall plot of the attenuation band. So these are like showing that where the attenuation bands are actually locating, and the white part is the propagation band, and the contour part, which is like a plotted in the with the contour map, that actually shows the strength of the attenuation. So here you can see, so we have also able to mark it very clearly. All the portion have their own equations because we are actually getting where the bands are locating, what are the equations for this portion, and where the peaks are coming. So each and every peaks can be traced properly, and so that actually helps you to understand for which parameter you can able to get a band margin. Like you can see here, like once you are taking a line at eta r equal to 0.5, eta r1 equal to eta r1 is one of the parameter, so that actually basically telling about the tuning of the parameter of the like the resonators and all those things. So you are seeing that 0.5, it's not at all, band is not marched, so you are getting like 3 discrete band, which actually make the things not good. Then if you see, if you are choosing eta r equal to 1.5, then you see that first 2 bands get marched. Like you see here also, like how they are getting marched here. So you are cutting it here, so these 2 peaks getting marched here. So you are getting a relatively bigger band, and also that level of attenuation is maintaining throughout, like a certain level of attenuation you are always getting. Now if you are going at eta r equal to 2, yes, your band is now quite big, because here that 3 peaks get marched. So you can see here also like how that thing is happening, like that blue line, gray line, and that green line all are getting marched at one point. So you are getting a quite big band, and so once you are designing a system like that, so your target should be to get this type of band gap where your system can perform fantastically, so that the system have their own good amount of dissipation in that level, and the things will be quite good. So in that sense, okay, so this should be like our goal to achieve. Okay, so with this we will complete this portion here. Thank you.